Now let's go into the fundamental limits of this technique. So as you remember, for the photo detection also, we found out about the short noise, and then we found out ways how we can detect below the short noise limit. Similarly, for these magnetometers also, there is a sensitivity measurement limit. So what we want to do, suppose we want to perform a task for a time t, and there are n atoms inside, and the coherence time is tau. What is coherence time? In this case, the coherence time is the time up to which all the spins will stay exactly in the same direction. So we have n rubidium atoms, and we have all of them aligned. And now we have done the performance measurement for time t, right? So the very first noise which comes is due to the probe beam itself. So we send a probe beam. Why we send the beam? Because this beam will go with a certain polarization, and the polarization will rotate because of the rubidium atom. But this probe beam, as I told you in my previous lecture, that the photon or the laser which you are using, they already have some sort of statistics. So that is this Poissonian statistics. And the same statistics also comes into the picture here, that when the light comes, it comes with some sort of fluctuation. And this fluctuation gives us the short noise. So we are already limited with photon short noise. The second noise which comes with the spin projection. So remember I told you that we have this number mj. Mj was the projection of your j. What is j? J is your total orbital angular momentum. Uh, so in quantum sense, if you remember this Stern-Gerlach experiment, that it is not possible to precisely measure the spin. When I'm saying that all the atoms have their spin aligned in one particular direction, there is definitely an uncertainty associated with that. It's not like all of them really have their spin in one particular direction. And if you try to find out how much is that uncertainty, that is the under root of n. So if we have n number of atoms, the limit for this uncertainty will be root n. That is the second kind of noise which is present here in the system. The third noise is also comes from the probe beam, but this time due to the polarization of the probe beam. And there is a name for it. It's called light shift noise. So actually the polarized beam, I told you that this polarized beam will come and it will interact with the atoms, and these atoms will act as birefringent material. So a circularly polarized, so a linearly polarized beam will come, and we can write a linearly polarized light with a combination of two circularly polarized lights. And for each of these circularly polarized light, the refractive index will be different. What is the meaning of that? The meaning is that the light can be split into two components. When it interacts with each of these atoms, light or photon will keep interacting. Uh, because of the polarization itself, it will start giving some sort of fluctuation in the signal. So let's say this off resonance light is going into this magnetic cell, and because of its polarization is not stable. Because when we say polarization in this particular direction, again the same problem, it is not really in that direction, it has also some fluctuation. And this polarization interacts with the material inside, which also has some fluctuation in its spin itself. Because of that spin, that birefringence is coming. And due to all this, there is one more noise coming into the picture, which is called this light shift noise. So there are three main noise. One is comes due to the polarization, second comes due to the photon statistics, and the third noise is because we cannot really tell which is the direction of the spin projection. So there are three fundamental noise in this system. And as I told you, the minimum in terms of angle we can go is 10 to the power minus 8, 18 radian, and in terms of the magnetic field which we can detect is in the femtotesla. So now let's go in the application domain. So what is the need of these atomic magnetometers? So let me give you the very first example, which is in the battery testing domain. So right now you have seen a lot of lithium-ion batteries. They are available in EV vehicles. They are available in mobile phones. And what is present in these batteries is lithium anode, and then there is a cathode, and there is some separator in between. What happens in batteries sometimes is that there is a sort of growth of this lithium, and this growth, because of that growth, there are some dendrites which you can create. What is these dendrites? Then they can actually go through the separate material which separates these two. And if it goes through this material and touches the cathode, this creates a problem. Now you have a short circuit. And because of that short circuit, the battery or your whole vehicle can catch fire, and the battery can also explode sometimes. So it is very important to find out whether this kind of things is happening inside the battery or not. Now the problem is there are methods to do that, and there are conventional non-destructive methods which are available. The very first method is X-ray diffraction. The another is neutron diffraction, and there is many more. So you can do these techniques, that is no problem, but every technique has some limitations. So first of all, these techniques are slow, and also the technique themselves can change the property of the material. And sometimes for, let's say, case of X-rays, they also involve harmful radiation. And you cannot really do real-time monitoring, that your vehicle is moving and then real-time you can monitor what is the performance of the battery, or is there any problem with the battery. So there are these limitations with these techniques, right? The another way is to destroy the battery and then try to find out. That is definitely absurd. There is no point of doing it. So the advantage comes here from the atomic magnetometry side, is that this is non-invasive technique. It's also non-destructive. You can actually apply this technique just um, when your vehicle is running or battery in use. That time also you can apply the technique. How you do it? So in your battery you have a lot of different materials. For example, nickel, cobalt, graphite. They all have magnetic properties, right? And once your battery works, some sort of redox reaction happens, and then there is movement of lithium ions. And because of that, lot of magnetic materials, or each of these materials have some sort of magnetic susceptibility. And what you can do is you can actually calculate this magnetic field, and by that magnetic field, you can back calculate the magnetic susceptibility. And then you can try to find out how much is your material is degraded as compared to a fresh material. You can compare what is the magnetic susceptibility that time and now. So you can calculate the induced magnetic field, and by doing that, you can calculate the susceptibility. The another thing is that actually inside these batteries, always there is a charge flowing, and because of that internal current, there is definitely some magnetic field, and this magnetic field can actually come out of the battery, so it is around the battery, and you need some sort of mechanism. So you can use atomic magnetometer, and you can actually find out the magnetic field. Now this magnetic field will change if there is some um, defects inside your system, or there is some non-uniformity, and by telling that, you can actually pinpoint the location of the internal defect. So you do a back calculation. You first calculate the magnetic field, and by calculating that magnetic field, you can back calculate the location of the defect. So it is called the inverse problem, and there are ways to solve these kind of problems. So that this battery is under operation, so it is doing some task, and during that task, you are checking whether your battery has some issues or not. So here is some sort of belt which you have applied, and you put your battery on top of it, and there is this plate which shields the external magnetic field. So you don't want any external magnetic field in this technique. Since your applied magnetic field or the magnetic field you are detecting will be very small, so you want any another magnetic field to destroy that or to come in between as a noise. Now, uh, because of the internal current flowing inside the battery, there will be some magnetic field. According to that magnetic field, which is, let's say, induced here, right, in these locations, you can actually calculate, you can put your sensor here and you can calculate this magnetic field. And because of this induced magnetic field, you can actually back calculate the depth, at which depth it is possible to have some sort of defect. So there are ways to back calculate the process, and you can really do it in situ. Like when the battery is there, you can battery is running, and then you can apply this technique to calculate. The another way is that, let's say, if some sort of dendroids or some other defects are there, so because of the defect, there will be some change in the magnetic field, and this magnetic field line will change, and then the magnetic field lines you can also detect using your sensor. So this sensor also has a three different type. One is scalar sensor, second is vector, and third is tensor. The scalar ones already give you only the magnetic field value. The vector ones will give you the field value together with the direction itself, and the tensor one is giving you the value in all three possible directions. So that is there are three different techniques. What I discussed was only the vector one. There is also the scalar and the tensor one, which we did not discuss, but this atomic magnetometer also works in different domains. So suppose if you have the tensor one, then you can actually find out in X, Y, Z, all three distribution of the electric field. In this case, we only see the magnetic field in the X, Z axis. So this axis and this axis. And what you see is some sort of dipolar characteristic. So that is one domain. The another very useful domain, or usually people use these kind of magnetic field in medicine or clinical studies. So you might have heard about magnetic resonance imaging, MRI technique. They are also based on the magnetic field. But today we will talk about this atomic magnetometer based technique, which is called magnetoencephalography. So we can also call it MEG just for the sake of simplicity. What is this MEG and what we want to do with this? So this MEG actually measures the magnetic field which are produced by the neuron. So let me show you a picture here. So that is somehow this is how the brain looks like, right? And inside this brain, if you look at this particular location, this is called cortex. And in this cortex, we have lot of neurons. They are aligned. So this is like this, like this. These arrows, they are all neurons, and they are aligned in a particular way. Now, what is a neuron? So if you zoom in one of these yellow arrow, this is one of the neurons. If you zoom in, what you see is that this is the direction, and all these neurons actually there is some sort of electrical pulse which is moving inside these neurons. So the signal in dendrites is quite high as compared to the signal which is in axon. So in the axon, the signal is high as compared to the dendrite. So we actually want to measure the magnetic field which is coming due to the electric field. And why electric field? Because all these neurons, they all have some sort, like in our brain, in our human body, spinal cord and all, suppose what we see, what we perceive with the retina, everything is going back to the brain in terms of electric signals. So we do have electrical signals which are floating in these neurons, and this is the structure of a typical neuron. And the electric current in the axon is not so high, but the electric current in neuron in dendrites is quite high here. But this whole presented one single arrow. So here you could see that in these areas, the neurons are somehow aligned. So the electric field will also be aligned. Like if some sort of electrical pulse or signal, suppose you suddenly get a shock or something, and then you will see that some electrical pulse, very high pulse will moving in your neurons, and they are all aligned. So they will also generate some sort of electric field. So you could see that this is how it looks like. So these are all dendrites, and that's the main axon, but the electric field is not good here. So the electric field is good in these dendrites. So as I told you, in the nerve cell, so that is the cell body. In the nerve cell, there will be a lot of ions flowing, and they create the electric pulses flowing, and they create electric current, and because of that electric current there is some sort of magnetic field. So you see that in this cortex, let's say in this direction, there is a lot of electric field here in yellow color, and then because of that, in the green you will see the magnetic field. All right. And so this dendrite current, which is in these things, that is dipolar in nature, and in axon it's quadrupolar, so it's quite confined. And in these ones, it's broader in nature, so spatial aspect is quite good. You can actually capture that. So I told you we dependent on dendrite current. And actually, roughly 10,000 neurons give you good enough current that you can actually get a signal outside of your brain. So you take 10,000 of these yellow arrows, whatever current they generate, corresponding to that, there will be a magnetic field, and that magnetic field will be good enough, which can come out of your brain, and we can actually detect it. So in the beginning, I showed you a diagram, and I told you close to our heart, the magnetic field is roughly 10 to the power minus 12 Tesla. Close to our brain, the magnetic field is 10 to the power minus 15 Tesla. So that is the field we are aiming to catch. And this field is generated by neuron, right? Now look at this brain. So that is some person. These are ear, and that is the brain. That is the cross section of the brain. You see here, because of these neurons, that is this blue color, that is the electric field line. Because of the current flowing these pulses, there is electric field. You see here, there is some sort of deflection here in these electric field. Here it's fine. What is happening is that this is our skull. Um, so that is the skull, and skull in human is dielectric in nature. It does not support electric flow. So because of that, what happens is that you have all these field lines getting distorted in this location. And here they are fine. There is no problem. So there is another technique which is called EEG. You might have seen people applying two electrodes on the brain, and then they can also calculate the electrical signal. So that is the technique which is depending on the electrical signal. But these electrical signals are not very good because the skull does not allow magnetic field to go out. And because of that, the magnetic field line getting destroyed or distorted. And because of that, the precision in EEG is not so good. That the another thing is that because of that current which is in this blue, there is a magnetic field which is in green, and this magnetic field is not getting destroyed by the skull. So if you apply MEG, this magnetic encephalography, then you can definitely you can capture this magnetic field out of your head, and then this is what we are trying to capture. So EEG is not that good as compared to MEG. Um, so what is the still it is okay, let's say, that we need to do magnetic field calculations, or we have to find out the magnetic field, but in which people it is very much important. Let's say we go for MRI. All of us might have gone to see a doctor, and we have seen MRI machine. But for example, in the kids, epilepsy is a bigger problem. So what is epilepsy? Epilepsy is nothing but some sort of low-lying electrical signals which are unwanted. Abruptly, they happen in kids, and then because of that, they have some sort of seizures and all. Um, so in epileptical people, actually, they have low-lying electrical activity in your brain, and one way is to give medicine. So kids or somebody who is having seizures and epileptical person, they can take medicine and maybe they will be fine. But let's suppose a worst case, if they cannot um, be cured with medicine, then what doctors have to do is that they have to remove that part of the brain which is creating this problem. So the part of the brain which is creating this electrical activity, unnecessary or unusual activities, they have to remove that part. But before removing that part, they need to know where is the part, like in which area of the brain is creating the problem. So the first task is to localize the problem, that you have to find out in which brain there is a problem. So here I show you the image. So in A, you see what doctors will do to a patient who has epilepsy. They have given medicine to this patient, but still the patient is not feeling better. There's a lot of problem going on. Now they have decided to open the uh, human brain. So they remove the skull. Once you remove the skull, that is how the human brain looks like. And now they take a net of electrodes. So there are a lot of electrodes, and they take this electrode and put it on the human brain. And then what they do is they take X-rays and all, and then apply different electrical voltage and all. They try to find out which is the area which is creating problem. So I told you we have to localize the problem. Now suppose a kid, and this process takes roughly 1 day to really localize the problem because it's a slow process. Now suppose a kid or a person whose head is open and 1 day is being taken by the doctor, area we have to remove, and then further they will do the surgery and everything. That is a very painful thing, and that is the problem which atomic magnetometer can solve. So what atomic magnetometer can do is that you need not to do a surgery and open the head and remove the skull. You can, without doing any clinical intervention or surgery, you can try to find out where is the location where this problem might be happening. So I told you there are different techniques. One is EEG. Its spatial resolution is quite poor in centimeters. So from one location on the head, you have to move, let's say, 1 to 2 centimeters away. Then only you can actually tell what is the problem. So you see that they apply the electrodes, and this distance between two electrodes, this is more than 1 centimeter. But the temporal resolution is good because like you get signals in milliseconds. The technique we are talking about is MEG. So this technique uh, has a better resolution, so you can get distribution in terms of millimeters. So temporal resolution is good, and it directly gives you neural activity. What do I mean by that? So for example, if you go for MRI, what MRI does is that it indirectly calculates the neural activity. So wherever the neural activity or some signal will be flowing, you will have a lot of consumption of the oxygen there. And what they do is that they track the consumption of the oxygen. And if the consumption of the oxygen is more, the blood will flow more there. So this is what they do in order to do the functional MRI or MRI. This technique is quite good in terms of resolution. You can even see in the images, you get very nice images, and you have the idea about the each and every section of the brain. But it's a little bit slow technique in terms of time resolution, and also comes with a very high cost. So still, this is the best technique till today. But there are a lot of applications which people can also do with MEG. So what we are discussing is MEG, but remember that in all these clinical procedures, this is the technique which is currently being used and is a bit more powerful. Um, so how they do this MEG is something like this. So in this diagram, they have made a system which actually looks something like this, but we will come back to it. So the basic principle is that I told you that they take a pump laser, which is 795 laser, and then the second laser is a probe laser, which is 780 nanometer laser. These are D1, D2 transitions of rubidium. Uh, so they apply these two lasers, and using some lenses, they try to focus both these lasers here on this collimating lens, and this collimating lens will send parallel beams inside the rubidium cell. So this is the rubidium cell, um, and a person will sit here by placing their head here, and there is some cooling element you have applied. And once, so you will see four spots, 1, 2, 3, 4. inside your rubidium cell, because you have two spots come from two lasers, and then the two comes from two different lasers. Uh, and then when light goes back, so this probe beam, you filter out the pump beam, and then probe beam, there are one, two, three, four photodiodes, and then you try to do the balance direction, as I told you, something like a homodyne direction. Then you try to find out the magnetic signal. This is how roughly it works. So this vapor cell is 4 mm. So this direction here is roughly 4 mm, and you have applied nitrogen also. Remember the quenching gas, so which is roughly 600 torr, and the total volume where you are going to sense is 20 mm cube. So the head will be here, and this much area will be important to capture something. So again, this is just the repetition of the same thing. So this was just the schematic, but in reality, this is how this device looks like. So these cables are these pump and probe beams. So lasers are there. These are optical fiber lasers, and then these lasers will go through this channel. And here you have your vapor cell, and then the light will go there. And there is this collimating lens, so it will try to make the parallel beams. The beam will go through the vapor, and then it will try come back. And here is this all the receiver optics and electronics. So you have all four diodes, and you try to do some sort of homodyne detection, or you can use a beam splitter to detect to do optical photometry. So that is the how it looks like. Um, and remember, since we are using two beam for excitation and two pump and two probes, so it's called the four-channel system. One, two, three, four. So it's a four-channel optically pumped atomic magnetometer for MEG. Now, uh, so this is how overall system looks like. That you also have to make a chamber so that you can isolate from the outer magnetic field, and then the person will sit here, and close to the head there will be a lot of these sensors attached. And what do you require in this system? As I already told you, we need lasers, we need some cooling, we need a vapor cell, we need electronics, we need different trigger systems. So when you do it in human, you have to give them some sort of trigger. So for that you need a trigger, and then you need some computer also to see what is happening. So here's a person. This person will go inside this chamber, and then there will be um, some sensors close to his head. They will touch him, and then they will try to check on this subject what is happening inside the brain, and try to localize the problem. So once this person goes inside this chamber, his head will hit one, two, three, four, five, six, these six channels or six sensors. So with six sensors, in each one of this there were four. So six into four, we have 24 channel array. And then once he's inside, this is how his head is touching these sensors here. So the right side of his head is kind of covered here. Now, what you have to do is that you can actually give two sort of signals. So let's first talk about this left part. So here what you have to do is you apply some electrodes to the wrist of this person here, and then you somehow give it some voltage. And then because of that voltage, the person will somehow do this to the thumb, or it will feel some sort of a pinch to the thumb. Once that happens, actually that is some sort of sensor or sensory signal. So in the brain we have different parts, and different parts have different functions. So this somatosensory region, this region is responsible once there is a some sort of pinching is happening, then the neurons will get activated here. And once the neurons get activated, there will be current, and then the magnetic field associated with it. So some 500 femtotesla magnetic field above the skull will be available, and then these kind of sensors will be able to get this. Another thing you can do is that you take the ear of the subject, and then you apply some 1 kilohertz of frequency to the now this temporal lobe part, this part of which is very close to the ear, roughly this part is there the neurons will get activated. and again you can calculate the magnetic activity close to this area. So different part responsible for different kind of neural activities, and you can calculate magnetic field for all different location, and then you try to find out what is going on into the brain. So this technique is not only for let's say finding out localized problem, but also you can other neuroscience related research using this method. So let's say on this subject, they have done two approaches. One, they have applied electrodes on the wrist, and because of that, some sort of twitching happened to the thumb, and then they detect the signal. The another is that they applied some frequency to the ear, and because of that, some stimuli happens inside the brain. Now this is how it looks like. So let's take the bottom example. This is for when you apply something into the ear, 1 kilohertz of frequency. So exactly what you are plotting, in y-axis there is time, and in the x-axis there is magnetic field. And what you do is you apply one time, you apply some audio signal to the ear, you measure the magnetic field with respect to time. You do again, then you measure again, then you do it again. So you do multiple measurements, and this is how these multiple measurements looks like. What you see is that at 100 milliseconds there is a peak. So now you know that at 100 milliseconds there is a peak. Now what you try to do is that, meaning there is roughly a high femtotesla signal close to 500 femtotesla at this particular time. Now you know the time and you know the magnetic field. Now you try to back calculate and create these magnetic contour plots. So by creating these magnetic contour plots, you can actually find out. So whatever is yellowish is the high magnetic field region, and whatever is the bluish is the low magnetic field region. And the bar is from 350 to 300. So 300 yellow color high magnetic field, 50 lower magnetic field. So by doing that, you can actually do multiple experiments, and for AEF, for these audio signals, you can actually find out that in this particular zone the neurons are active because we are getting very high electric field. So you can map it on the human brain and try to localize that, okay, if you have to operate, just go in this particular area because the activities are happening here. You should not go and, let's say, cut this part or that part of the brain. So this, I'm just explaining you in a simple way. There is a lot of physics and biology behind it. It's not that easy to one-to-one map the magnetic uh, contour onto the human brain anatomy. So for that also there is a lot of science involved. But in a simpler way is that you somehow know that, okay, magnetic field is present here higher because of those signals. So somehow for different signals, let's say for epilepsy patient, once these seizures happen, you take the measurements and then you find out in which part of the brain the problem is happening, and then you try to cut only that part and you damage the nerve there. So what they have done is that they did their technique MEG, and they tried to find out that white dot is this localized spot where the problem is happening, or this part was active due to this audio signal or SEF signal, not the audio, the other one. They try to do the same using SQUID also. So SQUID, I told you, this semiconductor quantum interference devices, they are also very expensive, but they are also very good. So they give the location where the red dot is, and when you apply the atomic magnetometer device, you get the location where the white dot is. So you see that there is a little bit of mismatch, but roughly you are very close. Um, so this technique is also very good in terms of localizing the problem. So now the doctor can go and try to check this only this particular section of the brain. So this, I told you, the resolution is below centimeter. So this might be some area where you have to focus to find out the problem. And with this, I would like to thank you for listening to my talk. And if you have questions and if you want to discuss something, please feel free to ask. Just drop the questions in the chat.
So thank you, Dr. Weber, for your talk. Now I request participants, like if you have any queries, please ask the questions through the chat so that they can be answered.
Yes, please feel free to ask questions. Also, you can ask questions from previous sessions, photon statistics, short noise, or any other topic which you had some issues. I have presentations also available on my laptop, so I can open and answer your queries.
So one again request for the participants. We have already mentioned during the start of lectures that all quizzes that will be opened from Friday evening to Friday for a week. So please wait till Friday. We are again opening previous two quizzes and new quiz that has been to be set. So you have a week time to submit the quizzes in this Diwali break. So I could not see any questions in the chat box. So let me thank speaker again for the talk. Yes, so presentation that will be shared and then we will upload it to the canvas. So third quiz is scheduled for Friday. Yes, right?
Including this first and second also. So all three quizzes, they will be available or open for submission during the Diwali break. All the certificates can only be issued by once all three quizzes are closed. Everybody has completed all these obligations. So we will be distributing the certificate maybe 10 days after the completion of the course, or 10 days up around 27. Okay. So okay, Vaibhav sir, thank you so much once again.
Yes, thank you, sir. Thanks a lot.
Yeah. So I think we can close it here. Thank you, everyone.
Sure.
I request our EICT Academy staff, please stop the recording and close the session.